I'm Tim Ventura, and we're joined today by Dr. Miguel Alcubierre, who proposed the Alcubierre Drive in 1994 paper as a theoretical solution to the field equations of general relativity to allow the creation of a Star Trek-type warp drive. Dr. Alcubierre is the director of the Nuclear Sciences Institute at UNAM and joins us today to discuss his vision for faster-than-light travel. So, Miguel, welcome. Let me start by asking what your inspiration was to become a physicist back in the day, and what further inspired you to write the paper proposing your model for the Alcubierre drive.
Yes, of course. My first inspiration to become a physicist was when I was around 14 or 15 years old. I actually liked a lot of astronomy. I started reading books about astronomy, everything I could get my hands on. I'm talking about the late 80s, so there was no internet. You had to go to the library to read about these things and find the books. It was not easy, but I read everything I could. And my dad actually, when I turned 15, he gave me as a present a small telescope, a 4-inch reflector telescope. So I would go out at night and look at the moon and the planets, Jupiter, Saturn, particularly Saturn is very beautiful when you see it even with a small telescope. The rings are fantastic. So at that time I started thinking about astronomy. I also started reading a lot of science fiction at the time. Initially Asimov and Arthur C. Clarke were my favorite authors at the time, so I read everything I could get my hands on from them. And Asimov was not only a science fiction writer, Asimov was also a popular science writer, and he was very good. He actually wrote excellent books about introductions to astronomy, for example, and I read that one. It was amazing because he talked about how the ancient Greeks learned about the stars and the motions of the planets, and then all the way up to the mid 20th century, which is when he was writing these things. So I became in love with astronomy, and by the time I was 17, I decided I wanted to be a professional astronomer. So I started finding out what I had to do in order to become an astronomer. And I discovered something that I guess a lot of people that have the same idea eventually discovered. Astronomy is not actually a career in the sense that there's no course in university that is just astronomy. All astronomers are first physicists. So in order to become an astronomer, you first have to become a physicist. So I said, okay, then that's the way forward. I'll study physics. So I went to the local. It's actually the National University in Mexico, but since I live in Mexico City, it was close to home. Actually, it's in the same city. So I went to the National University in Mexico to become a physicist, and I studied there for 5 years. During those years, I learned that most work in observational astronomy is not looking at beautiful things like planets and things like that. It's actually looking at things that I particularly found boring, which was measuring interstellar composition and things like that. So I didn't really like those things. I really was in love more with the theoretical sides, and I learned relativity when I was an undergrad student. And then I did a master's degree also at the National University in Mexico when I was about 23, 24 years old. And again, I took a course in relativity, in advanced general relativity when I was doing my master's degree. And I actually fell in love with the theory. I really liked the whole idea of general relativity, the whole idea that gravity is essentially just a manifestation of the geometry of space and time. I think that's one of the most elegant ideas in physics even today. And I fell in love with that. And I decided I was not going to be, after all, an observational astronomer. I was going to be more like a relativist, which is kind of an astrophysicist, but only sort of tangentially. I actually liked black holes and the Big Bang Theory, the origin of the universe, and those things, which is not quite astrophysics, or even less, because there was essentially no observational evidence for black holes. And even though we knew that the Big Bang was true, cosmology was actually only at its infancy, and we didn't have good data for cosmology even in the 80s. The data was very sparse. But I really liked the theory, so I decided this is what I'm going to do. I want to become a relativist and study general relativity, and I want to do a PhD in this subject. So I went to my professor in Mexico City, who had taught me he had given the course on advanced general relativity, And he told me, well, if you are interested in this, I actually did my PhD in Britain, and I have a very good, I had a very good supervisor, Professor Werner Schutz. So maybe I can write to him, and maybe he can receive you. And he did, and Professor Schutz actually wrote back saying, yeah, he can come. He needs to get some money because I don't have money here. But if he can get a grant from Mexico, then he's welcome to come. So I went there. I went to the city of Cardiff in Britain. Cardiff is the main city in Wales. It's not England. Never actually tell a Welsh person that he's in England because he won't talk to you again. I had to learn that again because in Mexico we tend to group the whole of Britain into just England, which is of course wrong. And then I went to Wales, to Cardiff, and I did my PhD over there. I started working in something we call numerical relativity, which is the way in which you can write the equations, the field equations of general relativity in a way that can be solved by a computer with a computer program, because the equations are extremely complicated. So solving them with pen and paper is really hard unless you have extremely high degrees of symmetry, like a completely spherical and static black hole, then you can solve them. Or a completely uniform and homogeneous cosmological model, then you can solve them. But as soon as you add a little complication, it's impossible to solve them by hand. So you need to solve them on a computer. So that's what I started working on in numerical relativity. Particularly at the time, it was the early 90s, we were interested in modeling the collision of two black holes, because we thought, and it's turned out to be true, that the collision of two black holes was going to be the most important source of gravitational waves. Gravitational waves had not been detected then. They were detected for the first time in 2015, and I'm talking about the early 90s, so it was 25 years before the first detection. But we're already interested in this, and my supervisor, Professor Schutz, was interested both in the numerical modeling of these systems and also in the detection of gravitational waves. He's one of the pioneers in the detection of gravitational waves. But even though he had students doing both kinds of things, my own work was more in the direction of this solution, this numerical solution of the collision of two black holes. And I worked on that for many years, the whole 90s actually. But while I was there, while I was in Cardiff, I'm also a fan of science fiction, as I mentioned earlier. I used to read everything I could get my hands on in science fiction. I also used to watch TV shows and movies about science fiction subjects. So I always liked Star Trek. Even when I was very young, we could see the original Star Trek series in Mexico on the TV. So I always liked it. And when I was in Cardiff, we were watching the Next Generation series, the one that started in the late 80s and early 90s. So I would used to watch that show with my friends. The other students, the other PhD students that were doing their PhD over there, they all loved Star Trek. So we used to get together on the Friday evenings to watch Star Trek. We would rent, it wasn't even a DVD, it was actually a VHS tape of Star Trek episodes, and we would watch it together. And one night when we were watching Star Trek, I started thinking about that, because they always think, in Star Trek, they always talk about moving faster than light, and they talk about something they always called the warp drive. The warp drive is a name that actually comes from science fiction, and it gives you the idea that warping is curving and it's deforming things. So it gives you the idea that if you want to travel faster than light, you need to deform space somehow, because in relativity, traveling faster than light normally through space is not allowed. Nothing can travel faster than light.
Yeah.
So I started thinking about, well, if they talk about distorting, warping space to travel faster than light, they never say how it's actually done, because it's just science fiction. So maybe there's a way to actually deform space that will allow you to travel faster than light. And I started thinking about this. I'm doing a PhD in general relativity. In general relativity, it tells you that gravity is a distortion of the geometry of space, it's a warping of space. So maybe there's a way to use gravity to warp space in such a way that it allows you to travel faster than light. There was already an idea about doing this that had been many decades old at the time, which was using something called wormholes, which is a sort of tunnel through space-time. You make a hole in one place and it comes out somewhere else. This is actually allowed in general relativity. It's very surprising, but it's allowed. But nobody knows how to make one, and it's actually complicated, because you need to punch a hole through space, and we have no idea how to do that. Even if in principle the theory allows you to do it, in practice we have no idea how to do it. But I came up with a different idea. I said, well, maybe instead of punching holes through space, do something else entirely. At the time, I was also studying a little bit about cosmology, and cosmology, which is the study of the evolution of the universe, you learn very early on that the universe is expanding. We've known that for about 100 years now, that about the expansion of the universe. And the expansion of the universe was detected observationally because the galaxies move away from you faster, the further away they are. But it was predicted theoretically before it was even observed. It was predicted in the mid-20s of last century. And it was predicted using the theory of Einstein's general relativity. Sorry, it was predicted by that theory. Einstein himself didn't predict it. I mean, he actually found that space couldn't remain static in a cosmological setting, and he didn't like it, so he invented something he called the cosmological constant to stop this from happening. But other people actually didn't like this idea of Einstein and explored the possibility of having a space that was expanding. So this actually a scientist called what was his name? I forget it at this time. It's terrible with names. Lemaitre, George Lemaitre. He was a Belgian physicist, and he explored this idea of having an expanding space. And he actually thought that if space was expanding today, back in the far past, it was concentrated in a very small region, which he called the cosmic egg, which is the first impression of what the Big Bang that we have today. So he didn't call it the Big Bang, he called it the cosmic egg. But we have this idea that space is expanding. And the expansion of space is very interesting because people tend to think that that's because there was some big explosion here and everything is just flying apart. That's not what happened. That's not the Big Bang. The Big Bang was the origin of space. There was no space, and space sort of started expanding everywhere at the same time. And the galaxies are not so much moving away from each other through space. They're essentially sitting there very quietly in their own corner of space, but space in the middle is expanding. Space is stretching. It's space the one that's doing the motion. It's not so much the galaxies. So space can stretch, and it can also contract. And we also had this idea in the 80s, something called inflation, which is the idea that in the origin of the universe, in the very, very early universe, the very first fractions of a second, the universe expanded very violently, exponentially. And this expansion meant that things that were very close together suddenly moved away from each other faster than the speed of light and were no longer in causal contact. They couldn't influence anymore each other. And this was invented to explain the fact that you can see when you look at completely different directions in space, everything looks exactly the same. And if you look at the background radiation of space, it looks exactly the same in different directions. And that didn't make any sense because these regions of space in an expanding universe have never been in contact. And if they've never been in contact, how are they so alike? So that this idea of inflation was invented to explain that. But that meant that you could actually expand space faster than light. And this doesn't actually violate any laws of physics. So I was thinking about these ideas, and then I said, well, maybe if you can expand space behind you very violently, like in the inflationary theory, then you will move away from whatever's behind you faster than light. And that's allowed in the theory because it's space itself the one that is expanding. But very quickly I realized that this doesn't help you because you want to get closer to the things that are in front of you, not so much away from the ones that are behind. So I said, well, maybe you can contract space in front of you, which is again allowed, is an opposite expansion. I said, well, combine both ideas. Maybe you can expand space behind you very violently, and in a completely symmetric way, contract space in front of you, and that will push you away from whatever's behind you and pull you towards whatever's in front of you, and you can do this faster than light. So that was the basic idea. It actually occurred to me in a half an hour or an hour after watching Star Trek on a Friday evening. And then next day in the morning, I went very early to the university. It was about 7 a.m. I was already there doing calculations, and I was using this computer package that allows you to manipulate Einstein's equations algebraically, not so much numerically, but it allows you to do calculations very quickly that would take you forever by hand. And after a couple of hours, I came up with a little set of equations that allowed you to actually have this kind of expansion and contraction behind you. And then I refined the idea over the next few weeks, and that's how the warp drive idea was born. I eventually went to my supervisor, Professor Schutz, and I showed him my calculations, and I said, I've done this. And I was afraid because I thought he was going to tell me, this is completely crazy, forget about it, and keep doing the black hole collision stuff that I told you, right? but no, he was actually very enthusiastic. He liked it a lot. He read it and he said, this is really nice, Miguel. So you should actually publish it. I had at the time I've never published a scientific paper. I was just doing my PhD. I was just a student. So he said, I will help you to draft a paper. So he helped me with the basic ideas. I drafted the first paper, and then when I took it to him, the title was boring. It said hyper-fast travel in general relativity. That was the title. And he said, no, Miguel, that's not gonna sell the idea. You have to put warp drive on the title. So I did, and that's the new title was the warp drive, and then the other thing was just the subtitle. And I sent it to a scientific journal. It was published in 1994. So that's essentially the history about the warp drive and how I got the idea.
Yeah, well, I mean, there are so many things that are absolutely remarkable about this. You'd mentioned Asimov and Clarke. Both of those were enormous influences for me as well. I actually corresponded with Arthur C. Clarke. We were working on an interview, but towards the end of his life, he got ill, and so we were actually setting things up, and unfortunately, his health declined, and that was. I think it was a great tragedy when he passed several years ago. But what intrigues me though is so with the Alcubierre drive. I mean, that's kind of the official name for it. But then at the same time, I think that the media and I think that the public imagination has really picked this idea up. And this is the vision for the Star Trek warp drive, and so it's interesting. You actually answered my second question because I was going to ask, did this come out of Star Trek? It sounds like that's kind of where you started. You were watching the show and you said, okay, here's this vision. How can we make this vision a reality? And so I think that the media really keyed in on that. And and again, that combined with the fact that your paper was a true hallmark. I mean, this was just a landmark paper in terms of, okay, here's how you build a warp drive, or at least here's the physics behind it,
Yeah, exactly. It is true that I was watching Star Trek. People then ask me what episode I was watching. I don't remember what episode. I don't know. There was something in The Next Generation, but I can't remember the episode. But yeah, I was watching Star Trek. So the inspiration came from there. And yeah, well, the other question you just mentioned it. People very often they ask me if I actually built or designed an engine, and of course I didn't design any kind of engine. This is just the physics behind the idea. No, I'm not an engineer. I have no idea how to design any kind of engine. It's just the physics behind the curvature of space that you would need this expansion and contraction of space. That's essentially what I did. It's actually a very short paper. The paper has only 4 pages, and it's been cited hundreds and hundreds of times by today by a lot of people that have worked on different aspects of the idea. It's not terribly practical. It might actually turn out to be impossible still in practice. But at the time, nobody had actually thought about this simple model, and which was in a way surprising that nobody had thought about it in many decades since the beginning of general relativity.
Yeah. Well, no, that makes sense, and I think the simplicity again. This goes to kind of that landmark aspect of it, right? Where you were able to just kind of make a statement and say, look, given these parameters, this is possible within this model. Well, so one of the things I wanted to ask was, you first proposed this drive back in 1994. I mean, science has continued to advance very rapidly since the original paper was published. Do you think that it is more feasible today based on advances in physics, or do you think that it may end up going kind of a different direction?
Yeah, it's not really more feasible. People have looked at it, and it has several problems, and we haven't been able to solve those problems, even though we learned more about the problems in the last 25 years than anything else. So it has a number of problems. One problem, for example, that I always mention is the fact that I knew this from the very beginning, from the original paper I mentioned it. In order to create this geometry, as I mentioned, gravity is the distortion of space and time, is the curvature of space-time, is what we call gravity. And gravity is produced by large concentrations of mass or energy. We know that mass or energy are equivalent since E equals mc squared, right? So we usually talk about energy. So you need large concentrations of energy to produce a significant distortion, a curvature in space. So I calculated the kind of energy you would need. And it came out with 2 very serious problems. The first one is that you actually needed something we call negative energy. And negative energy, as far as we know, doesn't actually exist. Uh, it might sound trivial, but since I mentioned energy and mass are equivalent, negative energy is equivalent to negative mass. And negative mass actually sounds really horrible. Mass is always positive, right? So we've never found anything in nature that has negative mass or negative energy. So it's not actually forbidden by the laws of physics. We don't know of any law that forbids negative energy, but we've never seen it. And all the theories, all the types of energy fields and types of matter that we know always have positive energy. Even antimatter or crazy, I don't know, all the nuclear forces, and they all have positive energy, not negative energy. So this is a serious drawback. There are small, extremely small amounts of negative energy allowed in quantum physics, something called the Casimir effect, which I even mentioned in the paper. But it allows very, very, very small concentrations of negative energy in very, very particular circumstances. So it's not clear if you can scale that to something that could be practical. That was the first problem, negative energy. The second problem that I also realized immediately was that you need huge quantities of negative energy. And you would need to turn the whole of Jupiter into negative energy to have something like a warp drive that is practical. But this is actually the best scenario. Initially, with the initial model I mentioned, people calculated that you needed about the whole energy content of the universe to create a warp bubble the size of an airplane. So it was ridiculous. But that's improved. Now you don't need a whole universe. You need something about the size of Jupiter to turn into a negative energy, to have a warp bubble moving at the speed of light that can contain something the size of an airplane, which is ridiculous, right? And how can you turn a whole planet into energy just to have one airplane move around? So the amount of negative energy is huge, and we haven't been able to reduce this significantly. So it's really hard, and even if you could, it's still negative energy, and we don't have negative energy. So it's two problems: negative energy and huge amounts of it. So those were the first two problems. There's another problem that I didn't realize immediately, but people realized eventually, and I actually saw it after a couple of years, but somebody published it before I did. So something is called the horizon problem, which means that if you're using this bubble to move faster than light, it turns out that the front of the bubble, since you're moving faster than light, if you try to send a signal from the spaceship sitting in the middle of the bubble to the front of the bubble, you can't. It will never reach it. It will get sort of stuck in the middle of the wall. So it will go a little bit further into the wall. I wouldn't be able to move forward because this signal is moving at most at the speed of light, and the bubble is moving faster than light. So you can't reach the front. And if you can't reach the front, there's a serious problem because you need to put some negative energy in the front, and you can't reach it. So how do you put the negative energy there if you can't reach it? So that's another problem. It's called the horizon problem. So because of these problems, I think it's probably not practical. I wouldn't say impossible, but maybe it will be impossible. But it's not clear at this time. But yeah, so things have gone bad. We haven't actually learned how to improve it. We've learned that it's actually difficult, and we've learned the problems. So that's one of the reasons I've never worked again on this subject. I only published the original paper in 1994, and I've never published another paper in it. Well, I did publish something about a couple of years ago with a co-author, in which both of us sort of made a summary of what people have learned over the past few years. So more than original research is more a summary of what has been learned in the last 20 odd years. But that's the only second paper I published on the subject. But as I mentioned, there's hundreds of papers that other people have published on the subject in which they analyze different aspects of these problems and different aspects of the geometry and things like that.
Yeah. Well, and it's interesting. I believe I might be mistaken, but I think Dr. Eric Davis did some papers where he tried to translate the physics that you did into string and brane theory. And that intrigued me. I think he did that back in 2006, 2007. But what intrigued me about that was, so he was taking something. I mean, it's an exciting idea to begin with, and I believe that was one of the first real papers on applied string and brane physics. So I mean, again, your work has influenced so many different things. So I guess I should also ask, it sounds like your colleagues were very supportive, and the media has had a field day with this idea. They love this idea, right? They love the Alcubierre Drive. But when you first published this paper, was it well received by the scientific community in general? And
It, it, Yeah, it depends. Some people were actually very happy and very enthusiastic about it, and other part of the community was not happy at all, and they thought this didn't make any sense at all. So yeah, in fact, the first journal I tried to publish the paper in rejected it and said this is nothing interesting, and this is not interesting, and it doesn't make any sense, so we won't accept it. So I had to go to a different journal, and eventually it was published in the second journal. But this is a typical reaction. A lot of physicists, so you will find that a lot of physicists don't like science fiction. You might think it's not the case, but that's not true. There's a divided camp. So there's a lot of physicists that love science fiction, and there's a lot of physicists that hate it. And so the physicists that love science fiction tend to like the idea of the warp drive a lot, and those that hate it tend to not like the idea at all, and they always keep on saying this will never work, it doesn't make any sense. So it was well received only by a part of the community, but that part of the community has worked on the subject, and as you said, it's been influential, and the paper has been cited many, many times, hundreds of times, of people working on different aspects of the idea. But yeah, there's still a rejection in different parts of the scientific community that just say you should be working on something more serious, which of course I have, right? So I've only worked, as I mentioned, I only wrote the original paper back in '94 and a second sort of summary paper a couple of years ago, but that's it. All the rest of my scientific career has been on more serious subjects like black holes.
Yeah. Well, and actually, so in terms of your career, I understand that your research involves numerical relativity. So you're employing computers essentially to formulate and solve Einstein's equations at the Nuclear Sciences Institute at UNAM. Can you tell me a little bit about this research? And then does that mesh well with the Alcubierre drive, or have you really just kind of moved on into different areas?
Yeah, there are different areas. I mean, what I do is, as I mentioned, during the 90s and early 2000s, I was working on the collision of two black holes, that modeling what happens when two black holes collide and the signal of gravitational waves that we emit. This problem was extremely difficult, extremely hard to solve. The first people that tried to solve this problem on a computer were back in the 60s, early 60s, and 64 is the first paper. But they couldn't do it. It's an extremely difficult problem, not only computationally, even theoretically. It turned out to be far more complicated than people thought. And it took the community 40 years to solve the problem. I was working on this problem all of the 90s and the early 2000s, and it was eventually solved in 2005, not directly by me, by other groups, but colleagues, very close colleagues of mine that eventually managed to do the first simulation of the collision of two black holes that move in a spiral and eventually collide with each other and emit gravitational waves. I actually did a lot of work on that area, and many of the techniques I developed are still used today in that. And I developed things about coordinate conditions and the way the equations should be written and numerical methods. So this was a community effort. There was probably about 100 people working on this subject during that time. Eventually in 2005 it was solved, and people are still doing these simulations today, but the simulation now can be done. So you just throw more computer power and more physics, complicated physics into it just to get more details. But the basic simulation can be done since about 2005. So after that, I moved on to other things, and I'm still doing numerical relativity today. But I'm studying more like gravitational collapse, which is when a black hole forms, how does it form? What happens at the moment that a black hole is being formed? What different types of fields can produce a black hole? So those are the research I've been doing in the last 15 odd years. I'm still doing that. I'm studying things that we call boson stars, which probably don't exist in nature, but they're a nice, interesting theoretical problem that you can solve with the computer. A boson star is a star that is not made of normal matter. It's made of something that we call a scalar field. Something like the Higgs bosons. You probably heard about the Higgs boson. The Higgs boson is a scalar field. And if we could produce a star made of that stuff, then that would be interesting. And I'm working on that kind of problems. And it's numerical work. I actually like a lot to program. I code a lot, and when I have free time, I like to go back to my code and tweak it and see what I can do with it, because I actually relax when I'm writing computer code. It's fun from my point of view. And I've been working on those sort of subjects, still numerical relativity, and which is what I've learned to do and what I really like. and these interesting things about gravitational collapse. I like also cosmology, but I've never actually done any serious work on cosmology. But I have very close colleagues that do it, so I talk to them a lot. But I've never actually worked on cosmology. And the warp drive is very different. The warp drive has nothing to do with numerical. I don't know of anyone that has actually done a numerical calculation with the warp drive. It's difficult because we don't know exactly what kind of matter would produce a warp drive, so we cannot put it in the computer to model it because we don't know what matter would do it. So it's not very closely related. But that's the sort of research I've been doing all my career. For a while, I didn't do much physics because, as you mentioned, I'm no longer am, but I was the director of the Nuclear Sciences Institute for 8 years.
Okay.
I stopped. I finished that in 2020. We only get to be director of an institute in UNAM for at most 8 years. So I did the 8 years and then I moved to something else. But after that, I'm going back to these calculations of gravitational collapse, something we call critical collapse, and different types of matter fields and energy fields.
Yeah, well, and I mean, some of the things that you're getting into this is so intriguing. I mean, the Alcubierre drive itself, and you talked about this earlier, right? You get the negative energy density, and it requires some form of exotic matter or the manipulation of dark energy, right? So, I mean, again, this stuff is really getting out there towards the edge of physics. But are there any insights? I mean, I'm not even sure if these things exist. Has there been any support for moving forward in terms of exotic matter or dark energy? Or
exotic matter, we don't. It's a very generic term. It can mean anything that doesn't satisfy the usual properties of matter. So it's too generic. Dark energy is very interesting. We don't know what it is. I don't think dark energy would be good enough for a warp drive. We need something even worse than that. But dark energy is extremely interesting in cosmology. We know that there's something out there that produces an acceleration in the expansion of the universe, which is completely unexpected. Even back in the 90s, when people discovered it, they discovered it observationally with measuring the speed of the expansion of the universe, and it came as a shock. Nobody expected this. We all expected the expansion of the universe to be slowing down very slowly. We wouldn't notice it in thousands of years, but if you can actually look at very far away galaxies, you should be able to measure that it's slowing down. And it turned out that it's not slowing down, it's actually speeding up, and this was a complete shock. And we modeled it using something we call dark energy. But again, dark energy is sort of like a generic name for whatever it is that's causing the expansion to accelerate. We have some simple models. The simplest model is just to add a special constant to the equations that is actually the constant that Einstein invented back in the 20s of last century, which is the cosmological constant. You add that to the equation, it seems to work. But people don't like it because it's just an ugly constant that has a very strange value, and we don't know why it should have that. It's actually a very, very small value, an extremely small value, and it doesn't seem nice theoretically. So people invent different kinds of energy fields that could do the same work, and that's what we call dark energy. So it's an exotic kind of energy that produces kind of anti-gravity because this accelerates the expansion of the universe, but we don't really know what it is. And I think that's one of the most exciting areas of physics, that whatever is dark energy. We have something else that we call dark matter, which is different. Dark matter is what creates the structure of the galaxies and the galaxy clusters. We don't know what it is either. So, and neither dark energy nor dark matter are part of the standard model of particle physics. It can't explain them. So if they exist, it's something else that we haven't discovered in the accelerators. We've discovered it only through cosmology. And I think that's one of the most interesting aspects of modern cosmology and modern physics. It's always more interesting when you don't really understand something, right? If you understand everything, it's nice and you can write the equations, but essentially the work is done. So it's much more interesting when you don't know something, because there's a lot of things you can try there and a lot of ideas. So yeah, but I don't think dark energy will help the world, right? Even though it is exotic matter in some way, but it's not exotic enough.
Yeah. Well, and it's interesting in terms of physics too. And this was something that intrigued me when I was reading through it. It was saying that to make the drive work, you proposed using solitary wave solutions, which are really kind of a form of soliton. And I'm a little bit familiar with that, right, in sonics. But essentially this is kind of a wave packet that the ship would travel within. So are the solitary wave solutions, are those consistent with general relativity? And are they supported at all by quantum mechanics or recent work in string brane theory?
We don't really know. Those are good questions. Well, we don't really know. We don't actually have a solitary wave solution in relativity in the sense of a soliton. I mean, we have plain gravitational waves, but that's not what we're thinking. We want something more localist. And that, as far as I know, we don't actually have solutions for solitonic waves in general relativity, quantum or not. And general relativity is mostly it's a classical theory. When you want to combine it with quantum physics, it gets completely messy, and nobody knows how to do it. I mean, the only solid result we have in quantum gravity, if you want, is Hawking's radiation, which is semi-classical. It's a kind of mix-up of quantum physics with gravitational classical physics, and you get that, but it's the only solid result we have. We don't actually have a good quantum theory of gravity, so we don't know if these things would be allowed in quantum gravity.
Interesting. Well, the reason I asked was, when I was reading about the solitary wave solutions, to me it reminded me a little bit of quantum wormholes, and I was wondering if there might be some similarities there or some kind of crossover. But I guess that gets super speculative. So
yeah, there's no, as far as I know, it isn't. I mean, people talk about the solitary wave solution for warp drive, but it's not. I think it's an abuse of language. It's not actually a solitary wave solution. It's a geometry that you build like you just propose this geometry, and then you figure out what sort of matter you would need. But it's not actually a solution in the sense that you're thinking about. It's not so I think it's just people call it like that because it looks a little bit like that, but it's not actually a solution in those sense. I actually don't like to call the warp drive a solution of the Einstein equations because it's not a solution. A solution is the other way around. When you solve the equations, you say, I have this matter, this distribution of matter, this energy field that has these properties, and then I solve to find what the geometry of space associated with it would be. And that's actually very complicated. The equations are extremely complex. What I did is the opposite way. I said, I like this geometry. What kind of matter I would need to create the geometry? And that's extremely simple to do. It just goes the other way. So it's very easy. So I don't like to call it a solution because it's not the right way to go about solutions. This is more like a designer spacetime. You like a spacetime with this geometry, and you design the geometry, and then you ask, is there any kind of matter that could do this? And that's very simple to answer. So wormholes is the same thing, right? So these are more, instead of solutions, they're designer spacetimes. They're nice geometries that you propose, and you see if there's any reasonable matter that could create them.
Yeah. Well, so when I was coming up with the questions, one of the things I'd wondered, I'm not sure if you've ever pondered this, and this would be kind of more engineering than it would be physics, but so in theory, we built the Alcubierre Drive. We're flying through space. We're at the speed of light. Does this warp bubble? I mean, are you going to have problems with like space dust and X-rays and gamma rays and all that kind of stuff, or do you think that those would flow around this bubble?
It would depend on the form of the bubble, but people have actually looked at this. Yes, in principle, if there's something in the middle of your path, a rock or something, and you hit it, even going slower than light, it's going to be really bad if you're going very fast. So if you're going faster than light, it's going to be even worse. So yes, you would need some to design the bubbles or deflect them, but I didn't actually worry about these things when I created the original idea. Yes, you would have also any kind of light that is coming towards you, it's going to be blue shifted towards X-rays or even gamma rays probably. So it's going to be extremely dangerous for you. So you need to shield the spaceship, of course, but these are practical questions that I never went into. I just wanted to see if the geometry would allow it. Also, people have looked at, for example, if there's radiation in front of the bubble, not coming towards you, but moving away from you, you would catch up with it. So as you catch up with it, all this radiation will accumulate in the front of the bubble.
Oh.
And when you stop the bubble, all this radiation will just keep going, and it's a lot of radiation that's accumulated there. So it would be dangerous to be in front of a warp drive even if it stops, because all the radiation will hit you. So yeah, people have looked at these things, but not myself. As I said, I was only interested in the main idea of the geometry, not so much the practical details.
Well, one of the reasons that I mentioned that, and I'm kind of driving towards this idea here. So with NASA, one of the things that they've done with their robotic probe program is at least recently, they've kind of gone away from manned space flight for a number of reasons. And one of those is smaller payloads, less life support, less
Yeah.
danger, right? I mean, they've got all the radiation issues and stuff like that. So, do you think that this drive would be more practical if you scaled it down? You could avoid issues with the blue shifting, the X-rays, things like that. Do you think it would be more practical in terms of
I,
energy if it was a smaller?
yeah, the smaller the better, and if you could produce a macroscopic warp drive, it would already be extremely exciting. Instead of sending people, if you could put a hydrogen atom in the middle just to check that if you can push something faster than light, that would be extremely exciting. And you could probably, if this turns out to be possible at all, if you could solve the problems of the negative energy and those things, you could probably test something like this in a laboratory instead of in space. You could set up a particle accelerator. You have a long tube, and try to move an atom through the tube or an electron faster than light. If you could create the necessary negative energy fields, that would be fantastic. And yeah, I've speculated about this, but I never wrote anything down. But yeah, I think that would be the way to do it. Even, and then you wouldn't even have the horizon problem. You have a tube, and this is going inside the tube, because you could generate the necessary fields from the outside. So yeah, that would be far more practical. And
Yeah.
if you do this, then you could send packages of information faster than light, and that would revolutionize information and telecommunications even on Earth. But as I said, at this point, it probably looks not practical at all. But
That
you need
makes
negative energy. You still need negative energy. It might not exist, and you would need huge quantities of it. Yes, you probably wouldn't need a planet if you're not moving a spaceship, but only an atom. But you would still need ridiculous amounts of energy just to move a single atom faster than light.
Yeah. So, Miguel, let me close by asking, what comes next for you and your research? What do you hope to achieve next, and where can we look for you in the headlines?
Well, I'm not actually looking for headlines. Well, I'm trying to do much more simple things. I'm looking, as I mentioned, at gravitational collapse, critical gravitational collapse. I'm interested in cosmology, and I'm interested in, for example, in what happens inside a black hole. That's something that I'm always very interested in. We have solutions for what happens inside a black hole, but they're sort of crazy. When you look at the solution for a rotating black hole, which we've known for 50 years, we call it the Kerr solution. The interior of the black hole is completely crazy. It has wormholes that lead to other universes. It has what we call closed time-like curves, which allows you to travel back in time inside the black hole. These things make no sense at all. So that probably means that what we think, these solutions for the inside of a black hole are wrong. So I'm interested in what can happen, and for that, you can probably model collapse of some real matter and see what would happen with the real collapse, and not with the solution of an eternal black hole. So things like that, I'm really interested in. So I'm going to keep working on that. I have my numerical codes. I'm going to keep waiting for the next foreseeable future, probably on gravitational collapse and the formation of horizons and singularities. That's what it's interesting to me at this time. I might eventually go do some work in cosmology, but I'm not an expert, so I need to learn a lot about it first.
Wonderful, wonderful. Well, Miguel, thank you so much. Thank you so much for your time. It is, sir, it is truly an honor to be able to interview you.
You're welcome. I'm happy to be here always.